In this lesson, we are going to learn how to solve double integrals over rectangular regions. Now remember, in calculus 1, you were given a continuous function of a single variable f of x over an interval a is less than or equal to x is less than or equal to b, and you were asked to find the area under the curve from a to b. So assuming we have this to be the xy plane, this is the y-axis, this is the x-axis, and then we have the function f of x producing this curve. So you are asked to find the area under the curve from A to B. And the area is given by the integral of the function f of x with respect to x from A to B. This is how to find the area under this curve from A to B. So in calculus 3, and for that matter in this lesson, you'll be given a continuous function of two variables in the form z equals f of xy, where this function f of xy is said to be greater than or equal to 0. That is, it is non-negative on the region R and in the xy plane. And you'll be asked to find the volume of the solid enclosed between the surface given by this function f of xy and the rectangular region R. So this time we are going to have the xyz plane. So this is the z-axis, y-axis, and then we have this to be the x-axis, and then we have a, b on the x-axis, and then c, d also on the y-axis. Now let's try to locate this rectangular region. So we are going to have this to be the rectangular region R, and then we also have this to be the surface formed by the function z equals f of xy. Now let's complete the solid. And so this is the solid S, which is formed between the surface given by the function z equals f of xy and the rectangular region R. Now, in this lesson, primarily, we are going to focus on finding the volume of the solid enclosed between the surface given by z equals f of xy and the rectangular region R. So the volume of this solid V is given by the double integral over the region R of the function f of xy dA, so over the region R, which is given by the set of all ordered pairs xy such that A is less than or equal to x is less than or equal to b, and then c is less than or equal to y is less than or equal to d. Now notice that the A can also be expressed as dx dy or dy dx. So for that matter, we have v equals the double integral of the function f of xy. So whenever you have the x dy, you realize that we have the x on the inside, and so we are going to have the integral from a to b also on the inside. We have dy on the outside, so you have the integral from c to d also on the outside. Now the moment you switch these two, you also switch the integrals. So this is also equal to the integral of the function f of xy dy dx. This time you have dy on the inside, so you have the integral from c to d also on the inside, and then the x on the outside, so from a to b also on the outside. The most important thing is evaluating the two produce the same answer. However, you should know that whenever you switch these two, the x dy, you also switch the integral. So basically, this is how to find the volume of the solid enclosed between the surface given by the function z equals f of xy and the rectangular region R. Now in the next section, we are going to consider a few examples. Notice that in this set of examples, we only consider double integrals over rectangular regions. So let's consider these examples one after the other. Now let's take our very first example. In this example, we are going to evaluate the double integral over the region R of the function for x squared y cubed dA over R equals the set of all ordered pairs xy such that 0 is less than or equal to x is less than or equal to 2, 0 is less than or equal to y is less than or equal to 3. So let's try this together. So we have the double integral over the region R of the function for x squared times y cubed dA, and we need to evaluate this integral or this double integral over the region R specified in the question. So we can equally express this as the double integral of the function for x squared y cubed dx dy. Now since we have the x on the inside, we have the interval from 0 to 2. So that's we have the integral from 0 to 2. And then because we have the y on the outside, we have the interval from 0 to 3. So we have the integral from 0 to 3 also on the outside. Now what this primarily means is that we are first of all going to integrate this function with respect to x, and then when we are done, we do that with respect to y. So we express this as the integral from 0 to 3, and this we keep on the outside, and then we have on the inside the integral from 0 to 2 of the function for x squared y cubed dx also on the inside, and then we have dy on the outside, meaning that we are going to perform the operation on x first. So we are going to integrate this function with respect to x, which means that we are going to keep the variable y as a constant. So we have the integral from 0 to 3 on the outside. Now we are going to integrate this function with respect to x. So we integrate with respect to x, thus we are going to increase the exponent on x by 1, and we divide through by the total exponent. So we have 4x cubed times y cubed, and then we divide by the total exponent or the exponent on x, which is 3. And then we have the limit from 0 to 2, and then outside the brackets we have times dy. Now in the next step, we are going to substitute the lower and the upper limits into this function, and so we are going to have the integral from 0 to 3 on the outside. First we input the upper limits in place of x, so we are going to have 4 times 2 cubed y cubed over 3, and then minus we input the lower limit in place of x, and then we have 4 times 0 cubed times y cubed all over 3, and then dy on the outside. So let's simplify this. We have 2 cubed to be 8, hence we have 8 times 4, which is 32, and thus we have 32 divided by 3 times y cubed minus. Now because we have 0 multiplying these values at the numerator, it means that this whole fraction is going to go to 0. Therefore we can still have 32 over 3 times y cubed, and then times dy. So because we have 32 over 3 as a constant, we are going to pull out the constant, so that we have the constant outside here times the integral from 0 to 3 of the function y cubed dy. Next we are going to integrate this function with respect to y, so that is basically equal to, we increase the exponent on y by 1, we divide by the exponent on y, and we have the limit from 0 to 3. Now this is equal to, we are going to have 32 divided by 3 on the outside, and then we input the upper limits in place of y here, so that we have 3 raised to the power 4 divided by 4 minus, we input the lower limit, so that we have 0 to the power 4 divided by 4. Now this is equal to, we have 32 divided by 3 times, into bracket, this fraction goes to 0, so we are left with 3 exponent 4 divided by 4. Now we can as well express this fraction as 3 times 3 to the power 3 or divided by 4. So 4 goes here once, 4 goes here 8 times, 3 goes here once, 3 goes here once. So we are left with 8 times 3 exponent 3, which is 27. And when you multiply these two values, you have 216. So this is the final answer. So basically, this is how to find the double integral of a function given over a specified region R. Now let's move on as we take the second example. So to example 2, we are also going to evaluate this double integral over the region R specified as the set of all ordered pairs xy such that 0 is less than or equal to x is less than or equal to pi, 0 is less than or equal to y is less than or equal to pi on 2. So we have the double integral over the region R of the function cos x plus 2y dA, and this we expressed as the double integral of the function cos x plus 2y dx dy. We have dx on the inside, so we are going to have 0 to pi also on the inside, and then dy on the outside, so 0 to pi on 2 also on the outside. Now let's try to work out this. So we are going to express this as the integral from 0 to pi on 2, and then inside we have the integral from 0 to pi of the function cos x plus 2y dx multiplying dy. So we are going to perform the operation on x. We are going to integrate this function with respect to x. So we have 0, the integral from 0 to pi on 2, and then on the inside we want to integrate this function with respect to x. So what we are going to do is, whenever you integrate cosine, you have sine. So we are going to have sine of the inside function, which is x plus 2y. Now, the next thing is we are going to differentiate the inside function with respect to x. So when you differentiate x with respect to x, you have 1 plus, because 2y is a constant, when you differentiate that, we have 0, and thus we have 1 plus 0 is equal to 1. Now this 1 appears at the denominator. So we have this divided by 1. We have the lower limit to be 0, upper limit to be pi, and then times dy. The next thing is we are going to input the upper and the lower limit in place of x in this function. So we have the integral from 0 to pi on 2, and then inside we have sine, that is in place of x we have pi, so sine pi plus 2y minus sine 0 plus 2y, and then times dy on the outside. So this becomes the integral from 0 to pi on 2 of, we have sine pi plus 2y minus sine 2y. Now the next thing is we are going to integrate this function with respect to y. So when you integrate sine, you have negative cosine. So we have negative cos. We are going to repeat the inside function, which is pi plus 2y, and then we differentiate this function with respect to y, and it appears at the denominator. So when you differentiate pi, which is a constant, you have 0, plus when you differentiate 2y with respect to y, you have 2. Therefore we have 0 plus 2, which is equal to 2. So 2 appears at the denominator. So all divided by 2 minus, when you integrate sine, you have negative cosine. So negative becomes plus. So plus cosine of the inside function 2y. Now we differentiate 2y with respect to y, and it appears at the denominator, that is equal to 2. And then we have the lower limit 0, upper limit pi on 2. Now let's evaluate this. So we are going to pull out the constant, which is 1 over 2 for each of the two terms. So on the outside we have 1 over 2, and then into brackets we have negative cos pi plus 2y, and then plus cos 2y from 0 to pi on 2. Next, we are going to input both the lower and the upper limits into this function. So we are going to have negative cos pi plus 2y. Now 2 times pi on 2, 2 cancels out 2, we are left with pi, so it becomes plus pi, and then plus cos 2y, that is 2 times pi on 2, 2 also cancels 2, we are left with pi, so plus pi, and then minus, for the lower limit we have negative cos pi plus 2y. Now 2 times 0 is 0, so we are left with pi here, and then plus cos 2y. 2 times 0 is also 0, so we have 0 here. Therefore, we have 1 over 2 on the outside. This becomes negative cos 2 pi, and then plus cos pi minus negative cos pi plus cos 0. Now cos 2 pi is 1, therefore we have negative cos 2 pi, that becomes negative 1, and then cos pi is also negative 1, so we are going to have negative 1 minus cos pi is negative 1 times negative 1, that becomes 1, plus cos 0 is 1, so this becomes 1 over 2 into brackets. Here we have negative 2 minus 1 plus 1 is 2, therefore we have this to be 1 over 2 times negative 4. 2 goes here once, 2 goes here 2 times, and then we have 1 times negative 2, which is equal to negative 2. So moving on to example 3, we are going to solve this double integral over the rectangle R defined in the question. So we have the double integral of the function x times the square root of 1 minus x squared dA over the region R. Now this is equal to, we express this as the double integral of the function x times the square root of 1 minus x squared dx dy, so that we have the interval from 0 to 1 on the inside and then 2 to 3 on the outside. Now looking at the nature of this function, if you try to integrate first with respect to x, the solution can look very cumbersome. It's going to be very complex. So let's try to integrate first with respect to y. So we say that this is equal to, now because we are going to switch the x dy, it means that we also need to switch the integrals. So here we are going to have on the inside from 2 to 3, on the outside from 0 to 1 of the function x times the square root of 1 minus x squared dy dx, and hence we can express this as, we have the integral from 0 to 1 on the outside, inside we have the integral from 2 to 3, and then we have the function x times the square root of 1 minus x squared dy times dx. So we have the integral from 0 to 1 on the outside. We're trying to integrate this function with respect to y. So in so doing, because we don't have any y term, it means that we are going to have y appearing. So we have xy times the square root of 1 minus x squared. We have the interval from 2 to 3. Therefore, we have the integral from 0 to 1, and then inside the brackets we are going to replace y with 3, so we are going to have 3x times the square root of 1 minus x squared minus, we are going to replace y with 2, so that we have minus 2x times the square root of 1 minus x squared times dx. So we have 3x minus 2x, that gives us x, so we have x times the square root of 1 minus x squared dx. Now we can express this as, that is the square root of 1 minus x squared, as 1 minus x squared raised to the power 1 over 2, so all raised to the power 1 over 2 dx. Now looking at this function, one thing that comes in mind is to integrate by part, is to do integration by part, because we have the product of two functions of x. Now if we want to integrate by parts, it's going to be a very long process, so we are going to do what we call u integration. So what we are going to do is, we are going to let, so let me do it here, we are going to let u be equal to this inside function, which is 1 minus x squared, and then in that case we have du dx to be equal to negative 2x. Let's try to find dx. So we have dx to be equal to, we interchange the positions of these two, and then we have dx to be equal to du divided by negative 2x. So we need these two, which are dx and then u. So we are going to put them here. We have the integral, and then one thing we need to take notice of is the fact that these are x values. So we have the lower limit x equals 0, we have upper limit x equals 1. Now since this time we are going to perform the integration with respect to u, it means that we need to change these x values to u values. We define u equals 1 minus x squared, so for x equals 0, we have u to be equal to 1 minus 0 squared, which is equal to 1. And then for x equals 1, we have u to be equal to 1 minus 1 squared, and that's equal to 0. Therefore, the limits change from 1 to 0, and then here we have x times 1 minus x squared is u, so x times u to the power 1 over 2, and then we have dx given us, or defined as, du divided by negative 2x. So x cancels out x, and then this is, we have a constant negative 1 over 2, so we pull out that constant negative 1 over 2. We have the integral from 1 to 0 of the function u to the power 1 over 2 du. Now in actual sense, we don't have a limit from a higher value to a lower value, so we need to work out this. Now to interchange these two values, it means that we are going to multiply this whole expression by negative 1. So we multiply that by negative 1, and then we have 1 over 2 times the integral from 0 to 1 of u to the power 1 over 2 du. Now we perform the integration on u, so that we have 1 over 2 times u to the power, we increase the exponent by 1, so that becomes 3 over 2 divided by the total exponent 3 over 2. Now when you multiply the numerator by the reciprocal of the denominator, you are going to have this to be equal to 2 over 3 u to the power 3 over 2 from 0 to 1. So this becomes 1 over 2 into brackets. Here you have 2 over 3 also as constant, so we can also pull that one out. So you are going to have 2 over 3 also on the outside, and then you have u to the power 3 over 2, so 1 to the power 3 over 2 minus 0 to the power 3 over 2. 2 cancels out 2, we are left with 1 over 3. 1 to the power 3 over 2 is 1. 0 to the power 3 over 2 is also 0. So finally we have 1 over 3. For example 4, we are going to evaluate this double integral over the rectangular region R. So we have the double integral over the region R of the function y sine xy dA, that is equal to the double integral of the function y sine xy dx dy. So from 0 to 2 on the inside, from 0 to pi on the outside. Now we further express this as the integral from 0 to pi on the outside, inside of the brackets, integral from 0 to 2 of y sine xy dx, and then on the outside times dy. So this is equal to the integral from 0 to pi. Now let's try to integrate this function with respect to x. So in doing so, we have this y here. Now whenever you integrate a sign, you have negative cosine, so it becomes negative y cos the inside function xy. Now here you have the function, the inside function, to be xy. So when you differentiate this function with respect to x, then you're going to have 1 times y. So the final answer is y. So we are going to divide this whole thing by y, and we have the limits from 0 to 2 and then multiplying dy. So this becomes the integral from 0 to pi of, now y cancels out y, so we are left with negative here, so we can pull out the negative, so that is the negative, multiplying the whole expression here. We are going to have cos xy, so in place of x we have 2, so that becomes cos 2y minus cos 0 times y is 0, so cos 0. So this becomes negative 1 on the outside times the integral from 0 to pi of the function cos 2y minus, now cos 0 is 1, so minus 1 times dy. Next we are going to integrate this function with respect to y. So we are going to have negative 1 on the outside, and then we have, now when you integrate cos, you have sine, so this becomes sine. We are going to repeat the inside function divided by, we are going to differentiate this function with respect to y, and that gives 2, so that appears at the denominator, minus, we integrate this with respect to y, and then we have y. Lower limit 0, upper limit pi. So this becomes negative 1 into bracket. Here we are going to have sine 2 times y, in place of y we have pi, so 2 pi divided by 2, minus, in place of y we have pi, minus, into bracket, we are going to have sine 2 times 0 is 0, so sine 0 divided by 2, and then minus 0. Now let's evaluate this. So this becomes negative 1 on the outside. Now sine 2 pi is 0, so 0 divided by 2 is also 0, so we have 0 minus pi, and then minus sine 0 is 0 divided by 2 is also 0, and then minus 0. So this becomes negative 1 on the outside times, this becomes negative pi, and then minus 0, which is still negative pi. When you multiply these two, you have pi. So we have the final value to be pi. In our last example, we are going to solve this integral over the rectangular region given in the problem. So we have the double integral over the region R of the function 1 plus x squared divided by 1 plus y squared dA. Now this problem is going to be very difficult to solve because it becomes very difficult to integrate either with respect to x or y first. Now what we are going to do is we are going to call on a property of the double integral to make it very easy for us to solve. Now this property states that if you have the double integral of a function f of xy dA, so long as you can represent this function in the form the double integral of the function g of x times h of y dA, then you can express this finally as the integral from a to b of g of x dx times the integral from c to d of the function h of y dy. So basically we are going to apply this here. So we have this to be the integral from 0 to 1 of the function 1 plus x squared dx, and we have this times the integral from 0 to 1 of the function 1 over 1 plus y squared dy. Now let's proceed with the rest of the solution. So we are going to integrate this function with respect to x. We integrate 1, we have x, plus we integrate x squared, we have x cubed over 3. Lower limit 0, upper limit 1, all times we integrate this with respect to y. Now when you integrate 1 over 1 plus y squared, you are going to have tan inverse of y. So from 0 to 1. Now this becomes, we input both the upper and the lower limits in place of x. So we are going to have upper limit, we have 1 plus 1 cube over 3 minus 0 plus 0 cube over 3. So upper limit, lower limit, times tan inverse of 1 minus tan inverse of 0. So this becomes, here we are going to have 1 plus 1 over 3, and that's going to give us 4 over 3 minus, this is 0. So we have 4 over 3 times. Now tan inverse of 1 is 45 degrees. In radians, that's going to be pi on 4 minus, this is going to give us 0. So we just ignore that. So finally, 4 goes here once, 4 goes here once, we are left with pi on 3. So we have our final expression to be, or our final value to be pi on 3.